Hi everyone, I am Richa Mudgur and I work as a senior bioinformatics scientist at Elucidata. In the next few minutes, I would like to talk to you about a machine learning approach called PeakML that helps in the classification of detected peak groups in metabolomics data analysis. So recent technological advances in mass spectrometry has significantly improved our capacity to obtain more and more data from each biological sample. This has also led the researchers to push the envelope and perform untargeted analysis and generate new hypotheses. However, this comes with many challenges, and one of the key challenges is to weed out the inherent noise in these data sets. As depicted in the first figure, one of the recent studies showed that out of the 25,000 iron features detected in LCMS samples, a large proportion of these were isotopes, adducts, contaminants, and artifacts, and it ultimately resulted in only less than 1,000 metabolites. So, to overcome this challenge, a common practice is that one would apply filtering methods. These methods predefine a very stringent threshold, which result in a handful but very high confidence features. However, there is a clear disadvantage of excluding out the low abundant features, and this limits us from exploring metabolomics datasets to its full potential. Without any of these filtering strategies, if we go ahead with manual curation, it is a very long and tedious process, which can lead to inconsistency in the curation strategy. Additionally, there could be variability between different experts, and that is also prone to more discrepancies and errors. So, the motivation behind this work was, can we apply machine learning methods that could enable us to address these challenges and weed out the noisy or the non informative peaks? To this end, we built a machine learning model that could mimic the user behavior and identify real signals from the pool of non informative peak groups. So, to begin with, any good machine learning model starts with a comprehensive training dataset. Here, we curated more than 6,000 peak groups of features and categorized them as good or bad. These were derived from 16 different datasets curated by 5 different experts. And these datasets include different acquisition methods and various vendors like SciX and Thermos and Bruckner. In order to extract a meaningful characteristic, we studied these two subsets in terms of what is the peak intensity, what is the peak shape, the symmetry, the Gaussian nature, the signal to noise ratio, the quality of the peaks, and even the cohort based. And then we encapsulated these in 88 different mathematical descriptors that we call peak attributes. So the figure in the top right shows the TSNE plot, or simply a dimensionality reduction plot of these peak attributes in order to identify any patterns or cluster in the data. What we see from the plot, it suggests that there is a combination of these attributes can be used to help us distinguish between the real and the noisy signals. So what we did, we used XGBoost algorithm, which is one of the most advanced decision tree boosting methods for building ML models. The cross-validation studies using this model showed a very high good performance accuracy, which was consistently in the range of 93 to 94%. So the model described here so far is built on data that was curated by 5 different experts. So what it tries to do is that it tries to capture the global nature of the peak curation. However, one of our previous analysis has shown that there could be a very high variability between expert to expert curation. And surprisingly, for some of the dataset, we could get a unanimous curation for only about 60 to 70% of the peaks in the data. So this begs the question, can we learn a new user behavior? And how difficult or how fast and accurately we can do that? For this, we came up with two different model frameworks. One is the continuous learning model, and the other is a personalized model, as what we can see in the bottom left corner. So when we talk about the continuous learning model, by taking just a few curated peak groups from a user, we built this upon the existing polypeak ML on top of it. Wherein in the personalized model, it is generated independently using like 2000 to 3000 peak groups that are curated by the new user. And what we found was that the CLM model outperforms the personalized model, and we can see from the bar charts for the 4 different data sets. So what it says is that with a minimal effort from a user for curating only a handful of peaks and which we built upon the our poly PeakML model that could outperform or at least have comparable accuracy for a model that is personalized or built only for that specific user, while retaining the global features. And finally, what we wanted to do was to address the age old question of human versus machines. We tried to compare the peak qualification of curation between a metabolomics expert with over 9 years of work experience to the ML output that we get for a higher resolution mass spectrometer. This dataset this dataset they used in this study was from cell extracts with had 9 different cohorts. The data was acquired by QExactive, operated on a negative mode with full scan after an elution of a 26 minute from a reverse phase column. And interestingly, what we observe is that given for the same dataset, the ML model performed with a very reliable accuracy of 94%. And then it also does this processing within minutes versus the hours devoted by an expert. And it also enables detection of new ion features that could eventually lead to new metabolites of interest. We also see value in the model as it is scalable and it is seamlessly integrated in LMAven for very easy use. And with that, I thank you all for listening.